So first off, we're not going to use the whole day today. I actually have to get out of here a little bit early to make an appointment this evening, which is fine because I think I sort of yesterday, what I covered yesterday is a little different from what I've been doing for that material with my other classes. So I think I'm actually kind of a little bit further ahead than I would be, so I'd probably be ending earlier anyways. But what I'm going to do is we're just going to make it, we're going to go on through, and I'm not going to take a break. And we might actually end kind of around halfway through or maybe a half hour after that. Taking a break would just, make us 20 minutes later getting out of here anyway. So we'll just go ahead and do this all as one session. Also, I might have said yesterday that I was going to update the makeup assignment exemptions this morning. I actually only got to it a little bit ago, but all of the makeup assignments are accurately exempted. So if you weren't sure about anything, you can look in the My Grade section and see a gray dot next to anything that you're responsible for. And
there's a makeup assignment for this class?
No, there's actually not really one. I could make it like there's the there is a nervous system makeup assignment, which is technically for yesterday's material, which I would probably use as makeup assignment for today, but since this is a weird day, and some people might not be able to be here because they have conflicts outside of school, like they might work on Thursday or something like that. So I'm not gonna use that makeup assignment for this section here. But that doesn't matter to you because you're here. You wouldn't have to do it.
Can I get a freebie?
No. Your freebie is that you're here and you get to experience all the fun of this last day of class. So, again, as I was saying yesterday, I had actually put the week 13 material in the week 12 folder, so I haven't changed these links at all. So this is what we did yesterday and the assignments that are associated with that. And then where it goes down, or it starts again with this week's goals, that's the week 13 material. There is a week 13 folder. I just didn't link to that. I just copied the stuff over here. So just a link to where in the chapter we're dealing with stuff this week is, and then a link to a website that is helpful for what we're covering. And actually, I do want to grab one thing real quick out of what we were talking about yesterday. Just this picture that we were looking at. But we're going on to this chapter here, which is on the neurological exam. And so I want to start by talking about a little bit in how I introduced this chapter. I've been using the neurological exam as a teaching tool sort of all along. I think it's a really good way to understand some rather complex things about the nervous system. Now, really, if you consider what we're doing here, we're studying how the nervous system works using our own nervous system. So there's this kind of recursive paradox to this. There's, well, I don't know how famous it is. I'm quite familiar with it. But there's a quote that I like to share that if the human nervous system were simple enough for us to understand it, we'd be too simple to understand it. Which is to say, it's a very complex system. And that complexity gives us the ability to experience our higher cognitive functioning, which gives us the ability to think about things and learn about things. But there is I don't want to say a limit so much, but there is a little bit of a paradox here. It's kind of hard to really entirely separate ourselves from what we're studying when we're using that to study it. So I'd like to use the neurological exam so that you can see some illustrations of what's going on with the nervous system. And it's a tool that's used in the clinic to assess neurological function. And what I like to stress about it in terms of this class is that it's also a way to link particular functions to specific regions that are responsible for those functions. And so in this overview part here it's talking about neuroanatomy and the neurological exam, and it introduces this term localization of function. What this means is that particular parts of the brain are responsible for particular functions. And I pulled up this picture that we were looking at last time, because we've already actually thought about this. I didn't use the term localization of function when I was talking about it yesterday, but all of these different little areas here are responsible for particular functions. And so we can say that, for instance, controlling the muscles to produce speech is localized to Broca's area. And if somebody has a lesion there, if they have a stroke, like I was mentioning for that YouTube video series that I mentioned, or the student I mentioned that I think he was in a car accident, whatever it might be, some sort of trauma that affects that part of the brain is going to reliably cause the same sort of neurological deficit, which is Broca's aphasia. There are other areas that are reliably linked to particular functions. That's the idea of localization of function. So we've already actually thought about that. Maybe the other one that I talked a little bit about yesterday was over here, and I can't remember exactly which location it is, but somewhere here in the temporal lobe is an area that's specifically responsible for facial recognition. And people can have a neurological deficit where they don't recognize faces. I talked about the guy, what was it? The man that mistook his wife for a hat. Did I mention that yesterday? Okay. So actually, if I didn't mention that at all, let me just real quick go to the video content section in Blackboard. In the nervous system section of this, this, I didn't talk about this, I didn't show you this. Wow, I really haven't.
Yesterday, yeah. Okay.
So this guy right here, he's a neurologist, and he wrote this book called The Man Who Mistook His Wife for a Hat. Did I talk about that?
No.
Okay. The video right here is him. This guy's Oliver Sacks. Oh, that's right. I'm thinking about the Monday group when I said all this. But his name's Oliver Sacks. You might be familiar with some of his work, and I'll mention that in a second. But this video is him talking about a problem he has called prosopagnosia, which means a face blindness, an inability to recognize faces. I sort of have this problem. I don't know if it's quite as neurological as what he's describing, but part of the reason why I have you give me a picture, I snap a picture of you for this, is because I have a little bit of trouble remembering names and faces. I was at the MS Walk this past weekend, and I saw somebody there. I'm like, could be somebody I recognize. Had no idea who it was. And then a little bit later, I passed her, and she goes, "Oh, hi, Professor." It's an old student of mine. I just couldn't place her because I didn't recognize her face. Now, slightly in my defense, she was wearing a hat and sunglasses because it was kind of warm and sunny out. And it was completely out of context. I don't normally expect to see students outside of school. So, so there was enough context for me to really place her, but I just completely didn't recognize her by face. So I don't think I'm quite as advanced as what he's talking about, but what he's talking about is some sort of deficit in that area of the temporal lobe. And then you might have heard of Oliver Sacks, or you might be familiar with him at least indirectly, because he's probably most famous for writing a book called Awakenings, which was made into a movie probably a couple of decades ago now. But it starred Robin Williams and Robert De Niro. And it's actually, the book, Awakenings, is autobiographical about this guy. When he first started as a medical doctor, he did research after medical school, and then he went into clinical practice. And his first position was working in a institution in Brooklyn, I think it was. And he found a population of patients there who were catatonic. They didn't seem to move at all. But he discovered that they actually could move, they just couldn't initiate movements on their own. And so there's a whole story about what's going on there. And that's what the movie's about. And so Robin Williams plays a character that's basically him, and then Robert De Niro plays one of the patients. It's really well done. The science is incredible because it's a true story and he wrote it. So that's, you might have heard of that movie, and that's his most public claim to fame. His second most famous book is called The Man Who Mistook His Wife for a Hat. And in that, and several books that he's written, he tells stories that are sort of about clinical experiences that he's been involved in. And so one of the stories is about a patient that he consulted for. It wasn't one of his patients, it was somebody else's patient, but his expertise was called on to try to figure out what was going on. And so he tells the story of what's going on with this patient in several meetings he had. It was actually a university or maybe conservatory music professor who started complaining about having problems recognizing his students, so by face. And so the story kind of hit home for me because I always kind of feel like I'm on the verge of that. But it got worse, and it went beyond just not being able to recognize faces. He started having problems recognizing all sorts of different objects. So the name of the book comes from an aspect of that story, which is he would go to visit Dr. Sacks with his wife at Dr. Sacks' office. And this was, I don't know, must have been in the 60s. And so a university professor at the time would tend to wear a hat wherever he went. And so he'd go in and he'd take his hat off and he'd put it on top of the coat tree in Dr. Sacks' office. And so at the end of one of those meetings, he's putting his coat on and he reaches to grab his hat, and he actually grabs his wife's head. Okay. And she just takes his hand and moves it over and puts it on the hat. And so Dr. Sacks asks about that episode, and she just says, "Oh, he does that sometimes." And I just, I know that he doesn't recognize things, and so he puts it over. He just knew that his hat was there. He remember putting it down, and it must be somewhere over here and about that height. So he grabbed something and thought it was his hat, because he couldn't recognize objects. So there was something there, and he grabbed it thinking that's where his hat would be. It was actually his wife's head. So he just couldn't be precise, or no, I shouldn't even say precise, but he couldn't recognize what things were. He just saw objects, but tried to rely on other cues to tell him what it was. And so he was basing it on height and his memory of where the hat would have been. And then his wife, just knowing the problems he had, just simply helped him find the thing. Anyways, that's prosopagnosia, which actually the story sort of starts with that patient's problems. This video here is an interview with Dr. Sachs about his own problems with face blindness. And maybe because of that particular patient, it's something that he's connected to there. So he tells the story. Anyways, the point of talking about that is that in this area here, and I can't remember precisely where, is the part of the body, part of the brain that's responsible for recognizing faces. So that function is localized to that area there. And other functions are localized to other areas that are depicted in Brodmann's map here. So with the neurological exam, we can look at how functions are localized. And I'm going to show you this picture in a second. But to introduce what the neurological exam is, I want to go to this website here. The link in this folder that says neurological exam website takes you to this page here. And I said earlier that I've been using this as a tool to explain neurological function in my classes for a long time. When I was starting out teaching anatomy and physiology at this level, I was looking for something online that would help illustrate. And I was looking for representations of how the neurological exams are performed and that sort of thing. I came across this website, and it's perfect for what I was looking for. In the middle there, underneath the logo that says neurologic exam, it refers to two doctors, one at the University of Nebraska and the other at the University of Utah, who have collaborated to put this together. The website, if you look at the actual address and link, will tell you that it's hosted by University of Utah, but it's a collaboration between these two people. Over on the left-hand side, this menu here runs through the different subtests or exams within the neurological exam. And we can see 5 here. There's actually 6. There's a 6th one down here. But the fact that it kind of cuts off on the screen here is useful because I only really want to think about these 5. And the 6th one isn't really a separate test of its own. It's really part of one of the other things in here. And it doesn't really fit with the anatomical connections I'm about to describe. So there are these 5 tests. There's what's called the mental status exam, which is basically higher functions, memory, orientation, language, those sorts of things. And then the cranial nerve exam, which is testing the nerves, how those 12 nerves function. And then the coordination exam, which is performing coordinated movements, whether it's walking a straight line or rapidly alternating between muscle groups to perform a function. And a very simple example of that is turning a doorknob. Moving your forearm back and forth, which is essentially going from pronation to supination, is flipping back and forth between opposing muscle groups. And to be able to do that repeatedly, that's a coordinated movement. Okay, so that's some of what that's getting at. And in fact, walking is really just a very complex version of that. With each step, you're extending one leg and flexing the other leg, and then you switch to flexing the first leg and extending the second leg, and then you switch back to extending the first leg and flexing the second leg. And that's just repeated coordinated movements, okay, walking. And then there's a sensory exam and the motor exam. Sensory the sensory exam is considering sensory input other than those things that are through the cranial nerves. So through the cranial nerves, you have smell, vision, taste, hearing, balance, and then touch, and that sort of thing for your face and neck. The sensory exam is specifically looking at the senses that are found below the neck. So that really just be anything that we tend to think of as touch in the rest of the body. And then the motor exam is sort of the other side of that coin, which is how we move muscles with anything besides the cranial nerve. So any movements that are taking place below the neck. So those are the 5 tests I want to talk about. This picture, which follows a little discussion of localization of function in the book, is just showing you a basic layout of the central nervous system. And the mental status exam is really concerned with what's going on in the cerebral hemispheres. The cranial nerves we see coming out here, and they're mostly coming out of the brainstem area. Cranial nerve number 1 is coming out of the cerebrum, sense of smell. Cranial nerve number 2 is connected to the diencephalon, vision. But then 3 through 12 are all attached to the brainstem. So mostly cranial nerves is concerned with the brainstem. And then coordination is really about the cerebellum. And then motor and sensory I just described as being about sensory or motor things happening below the neck, which is really associated with the spinal nerves and therefore in the central nervous system, the spinal cord. In this picture, motor and sensory are in specific locations on purpose. The anterior side of the spinal cord is responsible for motor functions. The motor neurons that we met several weeks ago now, that connect to muscle fibers at the neuromuscular junction, making the motor unit. Those neurons are found in the ventral or anterior part of the spinal cord. And then the sensory input, which is coming in through the dorsal root of the spinal nerve, is going to the dorsal or posterior part of the spinal cord. So motor is more anterior, sensory is more posterior for the spinal cord. So that lays out a broad generalization of where these 5 tests are really aimed. And so if somebody exhibits problems with mental status, it's a safe bet that something's happened to damage the cerebrum. If they're having problems with coordination, it's a safe bet that something's happened to affect the cerebellum. And if they can't move muscles in their body, then there's probably an issue with the spinal cord, okay, that kind of thing. So that's just a broad idea of where these tests are localizing, and so the functions they look at, we can localize within these areas. Now, there is a 6th test, like I mentioned, down here called the gait exam, but really gait is just another way of saying walking, and I just told you a little bit ago that walking is coordination. So gait is really just a subset of the coordination exam. It's not a separate thing itself. So really it's mostly considering cerebellar control of walking and also how the cerebellum controls motor output. But we're going to really just concentrate on these 5. In each section, it starts off with some information about anatomy. So going into the mental status exam, it lists information about the frontal lobes, temporal lobes, parietal lobes, occipital lobes. And then for language, there's actually areas of the temporal and frontal lobes that are responsible for that, which would be Broca's area in the frontal lobe and Wernicke's area around the temporal lobe. That's basically what that's getting at. And then each test has a section that says normal exam, and this lists the actual tests that are run. And in the list of anatomy that I just showed you a second ago, or here, you can click on one of these and it takes you to a spot on the page that explains what the test is, and then has links to show you a video of this test being performed. So this little thumbnail here shows two people, this guy here in a shirt and tie, and this woman in a polo shirt. The guy in the tie is actually one of the two people that was on the front page that I was pointing out, and he's acting like the interviewer, the doctor who's performing the neurological exam on a subject. So this woman is acting the part of the patient, but she's performing normally so that we can see what the test is supposed to look like. You can click on this link here and it'll stream the video for you. You can click on this and download the video, but you have to have a password to do that, which I actually don't have. I've been using this website for a long time, and over the decade or more that I've been using it, they've changed things about the website. They've updated and that sort of thing. This semester, this is the first time actually these two buttons have looked like this. It used to be one button said big movie and the other button said small movie. And so you could, just a matter of how big the frame was, which is essentially what the, well, I guess they downloaded them technically. But anyway, so they did this new, and they've also set up a password kind of protection to get into them. If I click on this to show you this video, it launches this and it says that I don't have the plugin for it. I haven't been able to figure out myself, and I haven't taken the time to contact the academic computing department here to find out why this isn't working, why that plugin isn't there. It's on the computer, it's just not playing through the browser. But instead, what I'm going to do is we're going to perform this. Okay, so who would like to volunteer to be the normal patient here? Okay. So I'm looking for my pen. So you can just stay there. It's just a verbal test, and you don't have to get up and do anything. You probably can't quite read what it says up there, but all it is I'm going to ask you to give me a list of words, to generate a list of words, to generate a set of words. That's the name of the test. The only rule is going to be that they all have to start with the same letter. So when I give you the letter, you're going to start giving me words back. They cannot be proper nouns. It can't start with a capital of this letter. It just has to be a general term. I've set a timer here for a minute, so I'll cut you off in a minute, but I might cut you off earlier if the set's long enough. So, what I want you to do is just give me words that start with the letter S.
Sing.
Stop.
Oh, stop.
Only me.
She's doing
one
this.
person.
One person.
I volunteered.
Okay. We're going to start that over, and I'm going to give you a different letter, which kind of screws up my plans here, but we'll go with it. Okay. So now give me give me words that start with the letter M.
Make. Might. Marry. More. Most. Many. Mall. Mall again. M-A-U-L. Maybe. May. Mop.
Okay, that should be fine.
Pretty good.
Yeah. So what the text there tells you is that the normal result is in a minute you should be able to generate a list of 10 words. And I think you have 11 or 12 there.
In like less than 30 seconds.
You have 11 words here. So you were normal. I did this for my night class. When would that have been? Week before last, I think, actually. And the woman that was doing that, I don't know if she had stage fright or whatever, but took her 45 seconds to get to 10 words.
I was gonna say mitochondria.
Oh,
I didn't know if that was
oh,
like proper, but it's not, definitely
no,
not. No.
but she did fine. Anyway, so that's a good sort of example of how a set of words can be generated based on that. Now, if you go to the abnormal examples section, the list of tests there actually didn't change. It flashed a second as it rebuilt the page, but we still have the same thing. So if we click on set generation, we get the same sort of spot, but now the thumbnail is of a different video. So this is it performed by somebody with a neurological deficit. Sorry? So for this particular guy, actually, if you scroll up, you can see that he's the subject of several videos here. He has a developmental disorder, which will be pretty obvious when you see the video. But there are some other subjects for different videos that are more appropriate to demonstrate what's going on here. Let me play this video, and then we'll talk about what it means. Now, I can't play it through this website here, but it actually is on YouTube. Sure, go ahead. Okay. So I just put in set generation and did a video search, and this is that video right here. So for some reason, the normal version from this website isn't on YouTube, but this version is. So let me just play this.
I'm going to give you a letter of the alphabet, and then what I want you to do is to just give me as many words to start with that letter, okay? So go for it. The letter is the letter S. Well, play and solve the law, okay?
Pretty good.
Oh, okay. Failure.
See here.
Oh, no.
Okay, so that was the abnormal example because he has a deficit and he isn't able to do it. Now, I've been using this website for a long time. I place the set generation ones as an example all the time. The first word he says, I can't be positive what it is. And if you put on the closed captioning, they don't know what it is either.
Somebody said set and then say. That's what I thought.
Yeah.
You said sexy. That could have been it too.
Well, in the closed captioning, they have S ... and then sophomore. So it's got to be just one word, and sexy is the only thing that makes sense
Right.
for what he's saying there.
Sensei.
Maybe. But if we look at what he did give us, it tells us something about what's going on with him.
Yeah.
He's imposed his own restriction on this. Now, he's not doing it consciously, but his brain is has a deficit, and so this is how it works. He's been told, just like I set up your example, to just give words that start with a particular letter. And the words he gives are all actually kind of related to each other. And if you look at the list you gave, you did more, most, many. Those are obviously related words semantically. You gave mall and mall, those are related because they're homonyms. Maybe and may, they're obviously related. So everybody does that. It's just he can't get out of that. That would be like if you started doing it, you said more, most, many, multiple, multitude, and you just couldn't do anything else. You're just coming up with them words that are talking about big numbers, millions, maybe something like that. Yeah. He's stuck on that. Now, he's being interviewed by the same guy in that guy's office, which I imagine is on the University of Nebraska campus. And so he was probably taken there or got there under his own means. And so in his mind, he's at a school. And so it's a little unfair. I'm reading a bit into this, but I think that sexy probably goes with the other words there because he's sort of stuck on this idea. He's out on this campus, and maybe he saw an attractive female student there, and so he's thinking she was a sexy sophomore, and that's where the words came from. I don't know if that's really what's going on, but it helps explain what that first word is as the only thing that I can think that he's saying there. And then he says school, he says senior. He then says, I'm done, I can't think of anything more. Now, he could have thought of maybe the word student, another S word that has to do with school, but that wasn't there. But he couldn't get very far. Now, actually, there's something interesting. If you listen to the what the instructions are for the normal and abnormal versions, and of course, I didn't play the normal version for you, but I gave those instructions. In both of the videos, he says, I'm going to time it for a minute. In the normal video, he says, I might end it earlier. And in this one, he never says that. So it could be that he's a little bit anxious. And he's thinking, I've got to sit here for a minute trying to figure out words that start with the letter S. And I've run through the 4 that can occur to me. And so he sort of panics. And he says, I don't know anymore. But if he'd been told to not worry about the time and things might end early if he does well, then he might have been able to keep on it. Now, the interviewer can't say, you still got 45 seconds or something like that. He's just given those instructions and he has to carry out what was asked of him. And so he opted not to continue that. So it might have been there's some anxiety in what he was doing. He's the subject of like 6 different videos here, so he might have been tired, having done several of these things. I don't know. But there's something different about what's going on in his brain. And I think the fact that he seems to be stuck on words related to his present circumstance. He's on this campus and what he might have seen on his way to the office or something like that. Might explain something that's going on. Now, if you go into the anatomy section here, or you, I think somewhere up there's another link that gives some information. Probably about half of what the mental status exam is testing is directed at frontal lobe function. And what this is dealing with, that's frontal lobe, is what we refer to sometimes as working memory or short-term memory. You have to remember what you're trying to do, words that start with the letter S, and you have to remember words that you've already performed or come up with. Those are short-term memory or working memory kind of things, which is a frontal lobe function. Also, directing the brain to find words is a frontal lobe thing. So in a normal brain, we learn things mostly by association. So, and that kind of goes to why some of these words are linked together. So you learn about what a sophomore is, because that's a student at school, what a senior is, those sorts of things. And so the brain can make those connections. But the frontal lobe has to direct that, at least to begin with. So he got that first instruction, he started looking for those words, but then the frontal lobe couldn't switch to find another set of words. Bonnie, you went ahead and came up with, what was that, more, most, many, but then your brain was very easily able to switch to finding other words that satisfy the same criteria. A normal brain's going to be flexible enough to move from one thing to another, and he's just stuck on the terms that seem to be relevant to his present situation. So that's sort of an example of the kind of things that are happening there. Now, if you're interested in looking at this stuff in more depth, you're welcome to. I just wanted to show you some examples using set generation, both the normal and the abnormal version. The website is meant for medical students at these schools to use to learn about the neurological exam, and so it has some additional stuff like quizzes for each section. You're welcome to look at that stuff. You don't need to do any of that stuff. I'm not asking you to complete work on there, but if you want to look a little deeper into the website, feel free. John?
Why did they use the S word? Like, why did they use words that start with S?
I think, I mean, it's just a random letter, kind of. And when I had to switch letters, I had to think about it. I didn't want to use, Q, right? Because that would be really hard for someone to come up with 10 words in a minute. So it has to be a fairly common letter. Probably you would want to start with a vowel either. But just somebody who's trained at doing this is going to have probably a set of letters that they tend to use, and they'll just cycle through them. I don't tend to do this, so I always sort of work with the S thing because that's what's in the video. But
I was just wondering if I had a couple ones saying use S.
they used S also? So I don't know if maybe that's the one that's used most often as an example. So when somebody learns about it, they see somebody doing it with S, and so they just all do it with S. But it could be any word. I mean, it could be any letter for what the test is looking for. There are some bad choices like Q, but it doesn't have to be S. That just might be the most common one that people use. Now, I do want to go through these other ones, not to show you anything, but I just want to jump to the list of sections for each one. So under cranial nerves, there's a lot of sections, because really what this is doing is it's testing all the different nerves. And there are several things you can do for certain nerves. So each one says cranial nerve and whatever numbers are associated with it. And then the specific test. Well, there are a few that don't say which nerves they're about. They actually are about certain ones. Now, we usually refer to cranial nerves by their Roman numeral. And here, everything's by the Arabic numeral, except for it says cranial nerve 2, visual fields, and cranial nerve 2, fundoscopy. Why they switched to Roman numerals for those two, I have no idea. But the fundoscopy one, at least, is actually not assessing neurological function so much as it is looking at the anatomy. And that's looking at the physical structure of the eye and also trying to assess if the cranial nerve might be physically affected. If there's a problem physically with a nerve, it'll push against the eye. And the fundus is sort of the bulging part of the eye that comes out. And if it's really bulging out, then that might be a sign of a problem physically with the tissue that makes up cranial nerve number 2. But otherwise, most of these other things are looking at functions. So cranial nerve number 1, that's pretty simple. It's the one for smell, so you just test somebody's ability to smell. People can lose a sense of smell for various reasons. Because of its location on the ventral surface of the frontal lobe, people that have some sort of frontal trauma to the head and skull can lose their sense of smell. I had a student several years ago now who, when I was talking about this cranial nerve, and I mentioned losing the sense of smell, he raised his hand and says, I lost my sense of smell about 3 years ago. And so I said, oh, did you have a car accident? Because that's the most common reason somebody has that. He goes, well, yeah, I guess you could say that. I was standing on top of a car. So apparently he and his friends thought it'd be kind of fun to stand on top of cars and try to stay on them while they're driving away.
Wow.
And so the car went driving off and he didn't have his balance or whatever, so he fell off. He hurt his on the ground. Had some pretty serious head trauma, and he can't smell anything anymore. So you can test for that. He probably didn't realize he couldn't smell anything after the trauma, so they probably did. They tested it. And in that situation, right when it happens, you can't be sure if it's permanent smell loss or temporary. If there's any swelling around the nerve, that might make it hard to smell right after the accident. But this is 3 years later, and he still can't smell. So he definitely damaged that nerve beyond repair. People lose their sense of smell as they get older also. It's an age-related condition sometimes. The biggest problem with losing your sense of smell is that it's really the main part of our enjoyment of food. The sense of taste is really pretty simple. There are 5 tastes. There's salt, sweet, sour, bitter, and savory, what's called umami. And really, sour and bitter are not really the most pleasant tastes in the world. Sometimes people want things to taste sour or bitter on purpose, but really they're meant to be signals that you don't eat something. If something's bitter, then it might be poisonous. If something's sour, it's probably overly acidic, like spoiled milk or something like that. So there's the savory, sweet, and salty tastes are really the only enjoyable tastes we have. And if that's all you have to enjoy food, it's really kind of bland. Most of what we experience is through the smell. So if somebody loses their sense of smell, they lose their enjoyment of food. And this guy was actually talking about that. If he eats pizza, the first bite or two are great. But then after that, he suddenly realizes he can't taste the pizza, and it gets really bland. The first bite or two is really his memory of what pizza tastes like.
Isn't it?
But he did share with us that he had a superpower because of this. He could tell how old the fryer oil was at McDonald's.
Because if he could taste it?
He could taste it, yeah. The lipids that are in fryer oil oxidize as they're exposed to heat. And they'll make the fries taste kind of bitter. Most people don't recognize it because it's covered with, well, not just salt, but other seasonings. And so it masks the bitter taste. But since he couldn't recognize the other seasonings, he could recognize the salt, but he couldn't recognize the other seasonings. And so he could recognize the bitterness associated with old fryer oil. So he's able to tell his friends when not to order the fries. That's not exactly an exciting superpower, but he had a superpower. He was proud. Anyway, so these are a bunch of different tests looking at the various functions of the cranial nerves. A lot of them have to do with being able to move the eyes. So cranial nerves 3, 4, and 6 are the ones that control the eye muscles. And so there's inspection, ocular alignment, versions, ductions, gaze systems, saccades, pursuit, nystagmus, vestibulo-ocular reflex, and vergence. Those are all looking really at how we move our eyes. Vision is our most important sense. Did I say that yesterday? And so making sure that our eyes are capable of moving properly is very important also. So you aren't eating, right?
Sorry.
So the easiest part of this kind of test is just the interviewer will say, follow the tip of this pen, and moves it through the visual field to make sure that both eyes are following the target together. One of the things that should be at the end of that is that the pen then comes in closer to the nose, and the eyes will converge on that, which I think is what vergence there is referring to. The thing about that particular test is that it's testing specifically cranial nerve number 4. When you look at something close to your face, focus can be tough. And to make focus work better, your eyes actually rotate a little bit. So they converge together, so you get kind of cross-eyed appearance, but also your eyes rotate in the orbits just a little bit. It's really hard to see because they're just adjusting within that space. But the irregularities in the iris, you can see them move when the eye rotates. So as the target's moving closer to the nose, just watching the irises and seeing them, if it changes, will show if cranial nerve number 4 is doing its job. That's really all that cranial nerve number 4 is responsible for. And it's a very, very minor function. I actually have trouble focusing on things closer than about there. And I don't know if it's because of this or because of something else. And I don't really care because it doesn't matter. There's nothing in life that being able to see fine focus this close to your face is that important. But it's how the system works. And when you're testing this function here, it's not really to see if you have that function, but rather it's about the anatomy behind that. The cranial nerve number 4 is the only cranial nerve that comes out of the posterior or dorsal brainstem. Everything else comes out of the ventral brainstem. So if somebody has problems rotating their eyes when they're looking at something close up, it might be because there's a problem here in the brain. That's the only test that can illustrate that. All of the other tests are looking at this area here. So the function itself isn't crucial, but the test can say, oh, you should probably look at other things related to this area. And the other things in that area are probably harder to test. But that can really get to it really quickly. Okay. A very easy one to explain, down at the bottom, cranial nerve number 12. That's responsible basically for moving the tongue. And the test for that is really simple. And usually when we think of a medical exam, it's usually the first thing that we think of. What's the sort of classic example of when a doctor is doing an exam?
Stick out your tongue.
And it's, yeah, stick out your tongue, say ah. And it's the sticking your tongue out part that's important. Yeah.
Oh, can you stick your tongue out? Okay.
Well, they say stick your tongue out and say ah, ah.
Mhm.
They're looking also in the back of the throat
skip
for
that.
tonsils and that sort of thing. But if you can't stick your tongue straight out, then that might point to a problem with cranial nerve number 12. You have 2 of them. You have a left and a right version of all of these. If there's a problem with one side or the other, then your tongue's not going to stick out straight. Instead, it's going to stick out to one side or the other. And the side it sticks out towards is the one that's got the problems. Your tongue has muscles in it. They're all, of course, attached to each other, so it all moves as one thing. The way that it works when you stick your tongue out is contraction of these muscles sticks the tongue out. If one muscle contracts and the other muscle doesn't, then the tongue's going to stick out towards the weak side. So that test actually gets at that function. And that's in a place that's important for, again, things that can be harder to test, but the cardiovascular control and respiratory control are in that same part of the brainstem. So if somebody's having problems sticking their tongue out, which is not, again, a crucial function to life, it might be a clue that there's something going on in that part of the brainstem that could be more dangerous than has to be assessed. It's a lot easier to just have somebody stick their tongue out than to spend time assessing all of their cardiovascular function and respiratory function. So these can be useful tests in that sense. Okay. The coordination exam, like I said, is about coordinated movements. And so we see repeated over and over here, rapid alternating movement. So for speech, for the hand, for the foot. And again, rapid alternating movement would be something like, flipping back and forth from pronation to supination. And that would be what hand rapid alternating movement is really getting at. But you can do that for speech or for moving the foot also. Because sending the signal from your cortex down to the brainstem or spinal cord, which is going to control those muscles, is continuously double checked by the cerebellum. So if you're having problems coordinating movements, the cerebellum will step in and provide correcting movements for that. So I said a little bit ago that walking is basically a rapid alternating movement thing too, and that's in this list here, it's what gait's about. So natural gait is just walking like this. If you're having problems walking normally, your cerebellum can take over and control that. Let's say you're walking and it's really windy and it's blowing you off balance. The cerebellum is responsible for helping you keep your balance while you're walking.
How about when you're drunk?
So that's the thing, is the coordination exam is essentially the,
DUI?
yeah, what is that called?
Right.
Field sobriety test, which I'm sure none of you have any personal experience with. But the Purkinje cells in the cerebellum, which were the cells that I showed you back with the tissue stuff that have that big dendritic tree in the cerebellum, they're very sensitive to alcohol. And so when somebody's drunk, you can see that because the cerebellum isn't able to function properly anymore because of, it's supposed to be in charge of a bunch of coordinated activity, and it loses its ability to do that. And you can see that very easily, and it's a quick way to test for the presence of alcohol. So you can see right there between hand and foot rapid alternating movement, it says finger to nose. Okay, that's putting your finger to your nose. Now, that's really easy to do if your eyes are open because you can watch your finger and get it to the right place. But if you close your eyes, then you can't really see where it is, and it's all based on the sense of where your body is in space. And the cerebellum can use that information to adjust the position of the finger. In the field sobriety test, often that's performed with the person tipping their head back, which is going to throw their sense of equilibrium off, which is another thing the cerebellum uses. And so they have to find their way here, and if they can't see it, they might be off. And that'll be a good indication of that. And walking also. The one that most people think of when you hear about field sobriety test is the say the alphabet backwards thing.
That's hard.
That is hard.
Yeah.
It's meant to be hard. Now, if somebody's drunk, trying to say the alphabet backwards usually makes them laugh or something, and that's kind of a tip-off. But really what it is it's getting at the speech rapid alternating movement. Now, down at the bottom of the screen, that's where it has the video for that. And in the description, it says having the patient say la, pa, ka can test rapid alternating movements of the tongue, lip, and palate. Those consonant sounds, la, pa, ka, or the L, the P, and the K, require alternating between different muscle groups to produce those sounds. That's rapid alternating movement. Now, in the field sobriety test, having the subject do that can be a little unusual, and they might laugh, and it might kind of throw that off, or the officer trying to perform it might not get the medical point behind it. But it's very easy by having somebody recite the alphabet. The thing is reciting the alphabet forwards doesn't require the cerebellum anymore. You've done that all your life. You're probably going to do it in that song. A, B, C, D, E. Everybody does that. You've learned how to control your muscles to sing that song to such a degree that your cerebellum's not part of that. You can sing the alphabet song when you're drunk probably pretty well. But going backwards does require your cerebellum to be part of alternating between muscle movements. So if you go Z, Y, X, W, V, U, T, S, R, Q, P, O, N, M, L, K, J, okay, that's far enough.
Pretty good.
That's pretty good because I've done that.
Yeah.
That's the third time I've done that the past couple of weeks, so I've been able to practice.
Oh, because you've been getting tested.
No, I've been
Teaching
doing it in my
class.
class. Actually, I only got back to Q last time I
Oh,
did, so I got past that because that's where I hung out last time. But and actually, I think I stopped at T the time before that. Anyways, so that's not something that you have practiced to the point that you're no longer using the cerebellum to control the rapid alternating muscle changes. So it's a better way of testing that, which you could do just as easily with nonsense syllables like la, ka, pa, or something like that. But it's just easier for somebody on the roadside to say, okay, say the alphabet backwards because everybody should know the alphabet. And a lot of people will say, oh, I can't do that when I'm sober. But it's pretty obvious if you're drunk versus sober trying to do that. Okay? So it's not really just the rapid alternating movement, it also gets at some cognitive functions, which can be compromised with drinking also. But those are, that's a coordination exam. Now, I just want to jump down to the gait exam real quick to point this out. If you go to the normal exam section of the gait exam, you have station, natural gait, and tandem gait, and then something called heel-to-toe walking. Going back to the coordination exam, station, natural gait, and tandem gait. There's not heel-to-toe walking in here, but that's just a variation on these gait things. So heel-to-toe walking is just putting your heel against your toe and stepping forward, which actually I have a problem doing because my legs aren't actually the same length because I had an accident as a kid. But those are really just subsets of this. The gait exam isn't really its own thing. So it's just in there. Now in the sensory exam and the motor exam, we're looking at sensory and motor functions associated with the spinal cord. And so sensory, we're looking at various aspects of touch, pain, temperature, vibration, position. Tactile movement is feeling things moving across your skin. 2-point discrimination is being able to see how far apart two things are. I have gotten very close to buying a little device to test this, just to bring into class. But it just has 2 plastic, not needles, but points at different lengths apart from each other, like a millimeter, a centimeter, that kind of thing. And how close together those 2 points are, that's 2-point discrimination. Okay. Graphesthesia is kind of like tactile movement. It's feeling stuff moving across your skin, but specifically drawing letters in this on the palm of your hand and the person recognizing them based on how they feel. Double simultaneous stimulation. If I remember correctly, that's about 2 points moving and being able to figure out that 2 things are happening at the same time. I don't remember what stereognosis is. That might be feeling the shape of things in your hand. Yeah, identifying objects. So most often it's putting coins or keys or something like that in somebody's hand, and they have to recognize them simply by what they feel like. So those are the kinds of things that are sensory, and some of the tests are going to target specifically upper or lower sensory experiences like upper and lower extremities there, and some of them are usually dealing with what we sense through our hands. I think graphesthesia can sometimes be done on like the back or the thigh or something like that to get different senses there, or different regions tested there. The motor side is going to look at strength, being able to move muscles, and tone, which is about sort of how the muscles feel. If you have muscle tone, that means actually the muscle's a little bit contracted all the time. Without muscle tone, the muscle's just completely loose and flabby. Okay? One thing that you can kind of learn about from the motor exam is whether problems producing movements are in the spinal cord or in the brain. There are two cells that are really responsible for any voluntary movement. There's a cell in your cerebral cortex in the primary motor cortex that I talked about last time that sends an axon down into the spinal cord, and it synapses on a neuron in your spinal cord, which then goes out and actually causes muscle contraction. Those two neurons are called the upper motor neuron and the lower motor neuron. And you can distinguish between diseases that affect one or the other through the motor test, and tone is a good way of looking at that. If the lower motor neuron isn't working, if there's no connection from the spinal cord directly to the muscle, then there will be no muscle tone. The muscle will be kind of flabby and loose. But if there is muscle tone, then the lower motor neuron is fine, and the problem's probably with the brain, the upper motor neuron. They also look at reflexes here. And reflexes really are about the combination of sensory and motor together. That's not in the sensory test specifically because it's sort of coming from comparing the two together when you're looking at where they go. Reflexes like this or down here. So those are looking at motor response kind of things, all of those. So that's just a quick explanation of some of the things that happen in the cranial, in the neurological exam. And in those different subsets of tests, you can direct information to where specific things are potentially damaged. Now, I want to go back to the book real quick and point out what comes after this. So this is talking about the idea of localization of function, and then this picture here sort of shows the major regions which each of those tests is localizing. But you can get more specific. If a particular cranial nerve function is compromised, or a particular sensory or motor function is compromised, you can tell where that is. And let me give you an example of that real quick before I go on to this next idea, which is a type of sensory discrimination. So I talked about two-point discrimination a second ago, which is telling how far apart two stimuli are on the skin. Now I want to talk about discriminating two types of sensations apart from each other. So I grabbed this dissection probe as a tool that will explain this. This exact thing would not be used to test it, but it would work just fine. There needs to be something with a dull end and a sharp end. And originally when I would talk about this, I'd use, and this is the more common thing that's used in the doctor's office, a cotton-tipped applicator, which basically means a generic Q-tip. The cotton end would be dull or soft, and then the other end can be made sharp because generic Q-tips, cotton-tipped applicators, are usually a thin wooden stick with cotton in one end, and if you break the stick in half, then where it breaks, there'll be a little splinter end to it, which would be like the pin on this. Now, the dull end or the soft end is going to give you sensations of touch, okay, the pressure against the skin as I'm pushing it there. The pointy end is actually a painful stimulus. Now, I'm not doing this very hard, just enough to sort of poke at the skin, but not actually making a hole in the skin. But that's a painful stimulus. So we can discriminate between touch and pain with either end of this probe. Okay. You can localize function using discrimination like this. So, before I show you the model, let me go to a picture in, I think it's in the somatic section. In the central processing part for the somatic nervous system chapter, it shows this picture that describes how sensory information travels through the spinal cord to get up to the brain. So it's central processing in the sense that it's going through the spinal cord and brain, the central nervous system. These two pictures are showing two different pathways that information travels into the brain. This one travels through the dorsal column, or the posterior side of the brainstem, spinal cord, and this one travels in a lateral position over here from the spine to ultimately the thalamus. And so down here, we have the dorsal column system, because this is the dorsal column white matter of the spinal cord. And this is called the spinothalamic tract, because this part of it starts in the spine and ends in the thalamus. Okay. They both originate with sensory neurons that are coming from the periphery. The dorsal column system, the sensory neuron from the periphery continues traveling through the spinal cord until it synapses in the medulla. In the spinothalamic tract, it enters in and it synapses right away. Whether it's from the medulla on this side or the spinal cord on this side, whatever the target of the peripheral sensory neuron is, that crosses over to the other side, okay? Because information from the right side of your body is going to go to the left side of your brain. So we see it crossing midline here or crossing midline there. And then it goes up and synapses in the thalamus, because everything has to go to the thalamus before it goes to the cerebral cortex. So these two pathways actually separate information. One stays on the same side of the spinal cord before it crosses over, and the other crosses over and goes up the other side of the spinal cord. Okay. Down here, it says what each is responsible for doing. The dorsal column system carries touch and proprioception, which says fine touch, which means this kind of touch, being able to feel things located on your body. And then proprioception is your sense of your body's location. And then the spinothalamic tract, or at least the lateral component, which is all that I talk about in the book, is carrying pain and temperature sensation, which means it's this sensation here. So you can use sensory discrimination to tell where things are happening. Now, usually when we think about spinal cord damage, we think about somebody who completely severs their spinal cord, like Christopher Reeve or something like that. But it's equally possible that that the spinal cord, which is passing through the vertebral cavity of the spinal column, might only be damaged on one side. So if somebody gets into, say, a motor vehicle accident, or most likely a motorcycle accident, the bone on this side of the vertebral column might be broken and get pushed into the vertebral cavity and actually damage the spinal cord. And it's not an uncommon thing to happen. Spinal cord damage isn't always all the way across. It could be that there's damage just on half of it. And not necessarily exactly half. It might be a little shy of midline, or it might be a little past midline. But it will distinguish between these two. So if damage comes in from this side and damages half the spinal cord, and it might go a little past midline or not quite to midline, but this fiber will be disrupted. Whereas if something comes in from the side, this fiber is on the opposite side and it's not going to be disrupted. You can use this sensory discrimination test to figure out where that is, to localize the damage based on this localization of function idea. The function is the sense of touch, whether it's the dull or the pain side, in various locations in the body. So let's say, because of how this model is set up, that right there is where the damage is. Now, motor function is going to be compromised. Okay? Motor signals are traveling down the spinal cord. And if we've damaged half the spinal cord, then that means that the motor functions on this half of the body are going to be lost, which essentially means that the person won't be able to move this leg, and they will be able to move that leg. And they'll be able to move both their arms because that's above the level of damage. But if we don't actually know where the damage is, movement doesn't tell us a whole lot. It just tells us the damage is somewhere in here. But the sensory discrimination can tell us exactly where the damage is. We can test discrimination between touch and pain with this probe, both sides. Now, what do you think the patient's going to say they experienced if we touch the non-movable leg with the dull end of this probe? Are they going to sense that?
Nothing,
Why?
because it's a non-movable leg.
The motor system sending stuff down is going down the same way that the dorsal column is going up. So that side's damaged. And what are they going to say if we poke them with the sharp part?
Nothing.
They will say, ow, that hurts.
Oh,
Really?
What? I don't get it.
Because the information from here goes into the spinal
Oh,
cord,
goes up the other
goes
side.
up the other
I
side.
get it. So it goes to other, okay. But
So-
if that's,
I don't get it.
if that's the damaged leg and it even goes up the other side, the information. Okay,
So
never mind. I get it. I get it.
the fibers coming down from the brain to control movement are coming through this part of the spinal cord. And the sensory information for touch is going up that same side of the spinal cord. But the information for pain crosses over and goes up the other
I
side.
see. I
So
see.
if damage is at this level, we're going to interrupt motor and touch sensation. But we're not going to touch, so to speak, the pain sensation. Okay. So this
Interesting.
will stay intact. And we can tell that with this discrimination. So they won't feel the touch on the leg that doesn't move, but they will feel the pain. Because the pain sensations cross over and avoid the damage. Whereas the touch sensation can't get past the site of damage on this side of the spinal cord.
So what if you put the pain on the other side?
Right, so if we go over here, what are they gonna tell us if we touch them with the dull end of the probe?
They won't feel. No, they will feel
They
it,
will feel it. They won't say ow, because it's not a painful
but
stimulus.
they won't feel it.
But they'll say, I can feel it.
Oh.
But then if we use the sharp side, what are they gonna say?
They won't feel it.
They won't feel it.
Okay.
Because that's a painful stimulus. It crosses over and tries to go up this side, but it can't get past the side of damage. They don't feel pain on this side, they do feel pain on this side. They don't feel touch on this side, they do feel, I said it wrong. They do feel touch on this side, they don't feel touch on this side.
Isn't that weird though? Because like, how do you decide what's like pain? Maybe it's not
well,
painful.
You consciously decide what's pain because pain receptors are activated.
Right.
So in your brain, all that's happening is electrical signals. You know what things are based on where they come from. So if they're coming from pain receptors, it's pain. If it's coming from touch receptors, it's touch.
Got
If
it.
it's coming from a photoreceptor, it's vision. If it's coming from a smell receptor, it's smell. There are experiments done in animal models that show you can reroute things and send information to different parts of the brain, and the brain will interpret that as a different sensation. For example, blind mole rats, since they're blind, they don't use the part of the brain that other rats would use for vision. So they send or they'd be touch, because they use feelers to feel what's.
Yeah, they have like those like. oh,
And so their brains are rewiring to accept information in different locations because they learn where things are. But if you do that to a regular rat and you make its touch sensors go to their visual cortex, they'll behave as if they're seeing something. They won't say, oh, cool, that looks great. You just train them on a visual task and they'll act as if it's a visual
Cool.
thing. And it's a very simplified version of what's going on.
It's cool.
Question?
This picture, I don't understand. These are the same spine on either side? That's like just the spine?
Right, so that's talking about you in your spine. The dorsal column system goes up the same side that the sensation comes from and crosses over to the other side of the brain of the medulla. pain enters and crosses over immediately wherever it comes into the spinal cord, and it goes up on the other side. Okay? So where things cross over is different, and you can use that difference to discriminate between touch and pain. Now, this applies to things that are coming through spinal nerves. So this is everything below the neck. From the neck up, these sensations are handled by the trigeminal system. But these types of sensations are still separated out. Trigeminal system, the fifth cranial nerve, is actually pretty extensive within the brainstem. Sort of all throughout the brainstem, there are nuclei that are processing experience of what sensations of what's touching your face. But you can discriminate between painful and dull stimuli with a probe like this, and people can say they don't feel the pain in certain areas, but they do feel the touch. And that's because within the trigeminal system, there's something like this. It's not anatomically like this. They're not separated out within the brainstem, side by side. Like somebody doesn't feel pain in the trigeminal system because it's going up the other side of the brainstem. That's not how the trigeminal system works. But different nuclei in the brainstem process pain or touch sensations. And so you can do touch discrimination on the face, just like I just described for the body, using the same sort of thing, and separate out those functions there. Any questions about this?
I still think it's confusing. Sorry.
Another way to kind of visualize this idea is images like this. Okay. So I just searched for spinal cord tract, and this is just a map of all of the different locations in the spinal cord. This is the dorsal column here, and this is the spinothalamic tract over here. Okay. This picture doesn't show you which side things are from. I just told you that. But information coming in from this side to the spinal cord goes into this dorsal column here. But coming in from this side, pain information, synapses in the gray matter right away, and then that sends its fiber over to this side and goes up the other side.
If it happens on the other side, it goes up the other side.
Right. So
Always the-
touch from this side goes up in the dorsal column on the same side. Touch on this side goes up in this dorsal column. Pain from this side crosses over to here. Pain from this side crosses over to here. Okay. So this
Why
picture
would
doesn't.
that- Why would that person not feel pain on the right side?
Because
The other side, and that's a damage.
Aren't both of them damaged on either side?
no, I was saying this is damaged to only half the spinal cord. I started by saying usually we think of the spinal cord damage as being complete all the way across, but actually if there's trauma to one side and say the bone fragments from the vertebral bone on one side get forced into the spinal cord, sometimes they'll only go part of the way in.
Okay.
That kind of thing. So that's probably the root of the
Sorry.
issues. You didn't realize I was talking about half damage. So yeah, this side of the spinal cord is damaged, then touch sensation in the dorsal column on this side is lost, coming from that same side. But pain sensation from the opposite side is lost also, because these fibers are reporting information from this side of the body. Okay. So I just searched for spinal cord tracts, and there's a bunch of different versions of this kind of picture. So I'm just showing you the dorsal column and part of the spinothalamic tract here. But there's a lot more, and I just didn't want to get into a lot of different things because I think this illustrates the ideas of how things travel from the periphery up to the brain pretty well. Okay. And in these, blue is the sensory stuff and red is the motor stuff. If you're interested. So the motor control that's lost because of that section, that damage on one side, is really these fibers here, okay? Because they're going to tell these neurons what to do. Any other questions? Okay. So again, this picture that I went to is actually in the central processing section of the somatic nervous system, but I just wanted to use that as an example of how the sensory exam can tell us something about where damage has actually occurred. But I want to cover something else today that's kind of more clinical than anything else, but it's back in the chapter we were looking at yesterday, which is anatomy of the nervous system. So after talking about the embryo last time, I went on to talk about the cerebral cortex, and we looked at these pictures here. I want to go on a little bit further and talk about what's happening in subcortical structures. So this picture is showing you a few nuclei in the cerebrum that are deep beneath the cortex. There are three things here. This thing right here, this thing right here, and this thing right here. And they're each labeled. So there's a caudate, putamen, and globus pallidus. The caudate and putamen, these two here, are actually two pieces of the same thing, which is called the striatum. And then the globus pallidus is another thing. These belong to a set of structures that are called the basal nuclei. And I want to talk about the basal nuclei a little bit more. Now, this picture shows a wiring diagram of the different parts of the basal nuclei and how they work. Before I get to this, I want to show you the other things here. So let me just see if I can get a picture of what I want from Google real quick. Yeah, here we go. So this is a picture of a real brain.
A slice.
Yes, a slice of a real brain, unstained. The caudate that I was just showing you in that picture out of the book would be in about this position. Okay, where this section's taken, which is about at the level of the brainstem, the caudate actually is pretty small, but there's a little gray matter right there. And then the putamen is this stuff over here. The globus pallidus that I just showed you in that previous picture is no longer, is barely visible. They've actually labeled it right there, but it's just a little chunk of it. That's all that's left. Okay. What I wanted to show you here is this black streak right here is what's called the substantia nigra, which means black substance. The neurons in here turn black because they have a chemical in them that is a black pigment. That's where they get their name. And then not labeled here, but might be that thing right there is the subthalamic nucleus. Okay, and those are all these pieces of the basal nuclei. And here's a picture that I have in the book showing the connections. Okay. As I was pulling this picture up, I saw another picture that I want to pull up, which is another way of representing the same information that I have in the book here. Okay. The caudate and putamen are lumped together as one thing because really they are a single structure. They just have a white matter separating them out, so they look like two things. But they're really one thing. And then the globus pallidus actually has two pieces, which are the external and internal segments. And then there's the subthalamic nucleus and the substantia nigra, which has two pieces, the pars compacta and the pars reticulata. The pars compacta is the part that's actually black. Pars reticulata is really just plain old gray matter. So this kind of shows the structures to some degree, and this picture up here is kind of a drawing of what I just showed you. So there's the caudate putamen, the globus pallidus, substantia nigra, and again, they don't show this subthalamic nucleus, but it's right by the globus pallidus. These structures are all kind of wired together, and this picture is trying to illustrate the connections, which can be a little bit confusing, and actually they seem to have left one thing out. So I'm going to go back to this picture, which is very schematic. The picture I was just showing you is trying to be kind of anatomical, but it gets a little hard to follow. Instead, I just have boxes representing these different parts. This is for the striatum, the globus pallidus, the putamen and caudate, or caudate and putamen. And then GP means globus pallidus, and the lowercase e means external segment. STN means subthalamic nucleus, and then GP for globus pallidus again, and then I means internal segment. And then SN stands for substantia nigra, and the lowercase c is for pars compacta, and the lowercase r is for pars reticulata. Now, before I go on too far, let me just write that down so you can see it all. So we'll refer to the striatum as a singular thing, but it really is these two parts. And then there's the globus pallidus, which has an internal segment, which we refer to as GPI, I, and an external segment, which is GPE. And then there's the subthalamic nucleus, which wasn't in the picture I was just trying to show you, but it's below the thalamus, hence the name. And there's the substantia nigra, which has two parts, the pars compacta, which is SNC, and the pars reticulata, which is SNR. So I'll come back and you'll be able to write that down if you don't have it all. I just want to go back to the picture for a sec, which is right here. So there's GPI, SNR, SNC, STN, GPE. Those are all the players there. Now, this other picture I was pointing out is trying to show you more of the anatomical connections or positions. And what I'm showing you here is very schematic. For one, this box right here is repeated down here. So we have GPI SNR and GPI SNR. Not that there's two of them, but rather that same thing is repeated because it's acted on two different ways. What SNR GPI is it's the output. It sends a signal to the thalamus, which is not part of the basal nuclei. It's what's receiving the information. The cortex is also not part of the basal nuclei. It's the input. So cortex sends information into all of this, and it gets information comes out to the thalamus. And then the thalamus can communicate back to the cortex and let it know what the basal nuclei said. The reason why this box is repeated twice is because there's really two parts of this. There's the direct pathway, which is striatum to GPI-SNR directly out. And then the indirect pathway, which is striatum to GPE to STN to GPI-SNR, and then out. Okay. Another way to have depicted this would have been maybe to put cortex to striatum to SNR GPI to thalamus, which then goes back to cortex. And then we have GPE and STN, which then can go to SNR GPI. Okay. So there's really only one thing that's SNR GPI. Just doubled there to show that there are two streams or two pathways. And then the other thing is SNC in here. Now, the two pathways, as I've depicted it here, are the direct pathway and the indirect pathway. Okay. And it's just a matter of how many steps there are between the striatum and GPI-SNR, which behave as if they're one thing. In the direct pathway, there's a GABA projection. So axons that synapse here release GABA. GABA is always inhibitory. So that means that these cells get inhibited, okay, when striatum is active in the direct pathway. What SNR GPI or GPI-SNR normally do is they inhibit thalamus with GABA also, the purple arrow there. When you inhibit something that normally inhibits, that's called disinhibition. It's a double negative. It's removing the inhibition. So the direct pathway disinhibits thalamus. And when thalamus is disinhibited, that's the same thing as saying thalamus is active. And so it sends a strong signal back to cortex. The indirect pathway, striatum inhibits GPE, which then disinhibits STN, which then releases glutamate onto GPI-SNR, which will then inhibit thalamus. Okay. So through a few steps, the end result of the indirect pathway is to increase inhibition of thalamus. Okay. And so thalamus will not send a signal back to cortex, and there'll be less activity. Now, the best way to illustrate what the basal nuclei are doing is really to look at motor function. So your motor cortex is trying to plan or decide how to perform a movement. It sends a signal into the striatum saying, here's what I want to do. And it waits for a signal back through the thalamus from the basal nuclei, telling it whether or not to do anything. If the thalamus is active, then the cortex makes that movement. If the thalamus is inhibited, it doesn't make that movement. So that means that the direct pathway, by disinhibiting thalamus, increases or causes more movement. The indirect pathway, by inhibiting thalamus, causes less movement. That's sort of the shorthand explanation of the players there. Do you get that? See that connection? Fill out a blank stares. Let me just write that down here. Direct pathway disinhibits thalamus and causes movement. Indirect pathway inhibits thalamus and causes less movement.
How is the thalamus involved in
It's just sending information back to the cortex, telling the cortex what to do. Okay. So it's sort of like if you texted a friend, asked a question, and your friend texted somebody else, and that somebody else told you the answer. Thalamus is just delivering the answer back. Okay. Actually, let me put the word more in here to be specific. Okay. So, disinhibits thalamus, causes more movement. Inhibits thalamus, causes less movement. Now, very easy way to illustrate this, and I say this in the book, but let me illustrate it here. You and I are both using our basal nuclei differently right now. I'm up and moving around. It's part of my lecture style. So my cortex sends the signal into my basal nuclei and says, should I get up and walk around while I'm talking now? And the direct pathway causes the thalamus to say, yeah, get up and move around. You're sitting there not moving. Kind of unfortunate characteristic of the lecture model of schooling. So your cortex is saying, oh my God, I got to get up and run around and do something. And the indirect pathway is inhibiting thalamus, and thalamus does not okay that information, doesn't send a signal so that the cortex will do that. And so you don't move around. That's a simple way of explaining the difference between these two pathways. Now the question comes probably very easily on that is, how does the striatum know whether to do direct pathway or indirect pathway? And the short answer, sorry?
Sorry, excuse me. What is this whole, like, all these pathways, like, what is the name of all of this?
The basal nuclei.
Okay, so the basal, when we said, I remember like maybe 3 classes ago when we started talking about this, we said nuclei were the
Right.
cells. Is that what we're talking about?
So the basal nuclei is describing these pieces of gray matter where cells are located. Okay. And they're called the basal nuclei because they're at the base of the cerebrum, sort of. Actually, an old-fashioned name for this is the basal ganglia, which if you search for information about this, you'll see that. They were called that before anybody really established the use of the word nucleus and ganglion in central versus peripheral. So textbooks are tending to call this the basal nuclei more often, but the old-fashioned name for it is actually basal ganglia.
And this is central.
Yes, this is in the brain, which is why I'm using the word nuclei. I just realized I misspelled nucleus here. So where was I? Back to this picture here. So the last bit of this is the substantia nigra pars compacta, which has an arrow representing dopamine being released into the striatum. And that's really what causes the basal nuclei to use the direct or indirect pathway. Dopamine has 2 types of receptors. There are D1 receptors and D2 receptors. One of them, and I can never remember which one, is excitatory and the other one is inhibitory. So when dopamine is released, it can either depolarize or hyperpolarize its targets depending on which receptor they have. So in the striatum, the cells of the direct pathway have one receptor on them, and the cells of the indirect pathway have the other receptor on them. So when dopamine is released, it acts as a switch. It activates one and inhibits the other, and I can never keep them straight. So I'm not trying to say it. That will hopefully lead students to say, well, what tells SNC when to release dopamine? And the reason I'm hoping people are thinking that is because that means that you're processing the information and trying to get to the ultimate questions. The answer, however, is going to frustrate you because I don't want to answer that question. It's complicated. But essentially, something like dopamine is part of a larger system within the brain that's about states of behavior or something like that. Dopamine, serotonin, norepinephrine, those kinds of things in the brain are usually big global changes. Like serotonin is related to sleep and wakefulness. When serotonin is active in the brain, you're probably asleep. With dopamine, it's not quite as simple as I'm going to say, but when dopamine's active in the system, you're more active, you're moving around more. And when it's not there, you're more sedentary or something like that. And it kind of directly goes to what's going on here, although there's other places in the brain that have dopamine. And I can't remember what norepinephrine was, but it's sort of that state change within the brain. So that's basically where the dopamine's coming from. And me, because I'm part of what I'm trying to do is to move around a little bit, my dopamine system is more active, yours is less active. Okay? Because you're sort of staying sedentary. Now, one way to really illustrate what's going on here is to talk about two disease states which are affecting the basal nuclei. The first one is Parkinson's disease. And in Parkinson's disease, the substantia nigra pars compacta dies, which means that the dopamine input to the striatum is lost. When that happens, the direct pathway becomes most active.
Can you say what dies again? Sorry.
The substantia nigra pars compacta, the box in the middle that releases dopamine. When the dopamine input is removed, the striatum's kind of locked into the direct pathway. And because of that, it causes thalamus to be disinhibited and the cortex to be more likely to produce movement. And the primary symptom that we associate with Parkinson's disease is tremors, and it's because of this. Now, actually, the symptom is more accurately intentional tremors. As the disease is progressing and more of the neurons in the substantia nigra pars compacta are dying off, the tremors get worse and worse. But it starts with somebody might not have tremors when they're at rest, but if they have to do something like pick something up, movement to cause picking something up is going to be processed through here. And if somebody's developing Parkinson's, when they start to move, they're going to start to see tremors because there's going to be more and uncontrolled activity associated with intentional movements. Okay. And then as the neurons in substantia nigra pars compacta die off further and further to the point of being completely gone, then the motor functions will become more persistent, and then there's more than just motor control that the basal nuclei are related to. So eventually, it'll cause other problems like attention and memory and cognition and all of those sorts of things. But we usually think of it in terms of the movement disorders, the tremor kind of thing. The other side of this, the other disease state that illustrates what basal nuclei do, is Huntington's disease. And in Huntington's disease, what happens is cells in the striatum die off. And so in that case, there's no input in the direct or the indirect pathway. But without input from the direct or indirect pathway side of the striatum, subthalamic nucleus becomes rather active. Wait, is that right? Scratch that, I'm not sure if that's correct. The point I'm trying to make is that the thalamus becomes inhibited more, okay? Which is really the point of what's going on there. And when the thalamus is inhibited, there's less feedback to the cortex, letting the cortex know when to move. Huntington's disease is also a motor disorder, and its primary motor symptom is what are called ballistic movements. So ballistic refers to, shooting a cannon. And so ballistic movements are going to be movements that are really sort of big movements like that. And think of it as somebody's, should I walk or whatever, and nothing comes out of the basal nuclei, but they still want to walk, so they have to overcome a lack of intentional movement. And so they really take a big step. That's like a ballistic movement.
So they'll look like that.
I don't know if what I'm acting out is a good representation of it, but I usually think of ballistic movements as being like reaching out to grab something and going.
Explosive movements.
Yes. That kind of. But I don't think I've ever actually seen a depiction of it. Just read about it. So, but those two disease states are kind of the extremes here. Parkinson's disease is like the direct pathway is stuck in the on position. And Huntington's disease is like the indirect pathway is stuck in the on position. And for your average person, it fluctuates between the two because of how the dopamine input switches between the two there. Now, all of what I just covered actually is in the book. I explain it all kind of the same way, but it is confusing, so I wanted to go through it so you've heard it. But you should sort of get a repeat of all that information in the book. And so you can look back to that. In case you didn't get all the stuff I wrote up on the screen, I'm going back to the screen now. But if you have any questions about this, hopefully this explanation clears some of it up, and it's just repeated again in the book. And I think it's the kind of thing that you need to hear a couple of times. Yeah.
This is like mainly about a pathway about movement. It's mainly.
Actually, the basal nuclei connect to all parts of the cortex, so it's about all cortical function. However, it's usually discussed in terms of movement, okay? Especially because these disease states are usually mostly about movement disorders. But Parkinson's and Huntington's disease, when they get to an extreme, to an advanced stage, are going to see broader cortical function loss, including memory, cognition, those sorts of things. But, so we usually talk about it in terms of motor, but it's broader than that. There's just not a really good way to explain other cortical functions tied into it beyond the motor. So any reference you find about basal nuclei, I'll talk about it in terms of motor function. Other questions? Okay. I do want to say one last thing about Parkinson's disease. When somebody's diagnosed with Parkinson's disease, we don't know what's actually causing it. So something is killing the neurons in the substantia pars compacta. We just don't know what's actually causing it. But some people will present with symptoms like Parkinson's disease, but we know perfectly well what's causing it. And so that's not officially Parkinson's disease. It's referred to as Parkinsonism. There are two celebrities that are associated with Parkinson's these days. There's Michael J. Fox and Muhammad Ali. Now, Michael J. Fox has Parkinson's disease because they don't know what caused it, and it's rather unfortunate. It tends to set in on average in somebody's 50s, but for him it was in his 30s. So he has a rather extreme version of it. But he's also doing a lot to manage it. Fortunately for him, he can continue working because now he tends to play characters that have movement disorder type things. If you've seen him, he's in The Good Wife these days.
He seems okay. Like, maybe I haven't seen him in a while, but I was looking, he seems okay. Like, he seems like he kind of, not that he's okay, it's Parkinson's disease, but seems like he controls himself, or Maybe it's
Yeah.
medication.
So he's on medication. I think he's getting a brain stimulation treatment, which can help too.
Cool.
And then also, he's a very physical actor, so he can translate a lot of the symptomology into how he's acting.
You can mainly notice it in his speech, like it's the main part of the.
But like, I think of when he was, if you've not seen the show, whatever, but he was the main character in a show called Spin City.
I remember Spin
Wow,
City.
that-
Yeah.
He was a very physical character there. And I think what it was is a lot of times he was covering up the symptoms. So you'd often see him sit on the desk and he'd be sitting like this.
Right.
It was to kind of make his body not behave like that. Now he's in The Good Wife and the character has a movement disorder. And it's actually kind of a running joke that when he's,
He always used that.
yeah,
in
he
his-
starts off talking to the jury in the courtroom by saying, I have this disorder. It's like he's always trying to win over the jury by them feeling sorry for him. So,
Disability, right.
but yeah, so he has his ways of coping with it, and if I remember correctly, he's actually using this deep brain stimulation treatment, which has been somewhat successful with Parkinson's patients. Now, I said Muhammad Ali is also associated with that too, but he doesn't have Parkinson's disease. He has what we would just call Parkinsonism, because we know exactly what caused it. His profession. You will often see boxers with tremors because the substantia nigra pars compacta, for some reason, is a rather fragile nucleus. So if somebody gets hit in the head a lot, since it's located in the brainstem, it's right where the head's going to be moving around a lot with repeated blows to the skull. So it's not unusual for people to present with tremors if they have a boxing kind of career. Probably you see some of that stuff with football players that are getting hit on the head a lot. I'd imagine that mixed martial arts fighters, those kind of things. Yeah, they're real wrestlers, like Olympic kind of wrestlers,
No,
probably
no.
not so much. But yeah, the television wrestlers where they do all sorts of things.
Hockey players.
Yeah. Yeah, that kind of thing.
Oh, yeah.
So you probably see those kind of things, but we can pretty much say all of those are caused by their blows to the head, and that's not technically Parkinson's disease.
Oh, yeah. Football.
I mentioned earlier Oliver Sacks and the movie Awakenings that's based on his experience, and what's described in the Awakenings, that disease, is actually a type of Parkinsonism. The characters in the movie and the real people that it's based on all suffered the same kind of encephalitis when they're kids. And the virus or whatever that caused that when they're kids damaged this part of the brain, and by the time they became adults, they started having sort of severe tremors. And in the movie, Robert De Niro's character, actually the kid playing the younger version of that, there's this really heartbreaking sequence where he's trying to write his name and he gets tremors from that. But what happens is that the tremors get so advanced that opposing muscle groups are trying to contract at the same time, and it locks the body up. But the treatment that they use in Awakenings is a treatment that you'd use for Parkinson's disease. The problem is back then, the drug that was used just increases dopamine levels in the brain. And while that'll help Parkinson's symptoms for a little while, it'll also cause an onset of schizophrenia, which is kind of an extreme dopamine psychoactive disorder. So taking them off of the drug alleviates the schizophrenic symptoms, but then also they go back to having the problems. And that's actually part of the drama of the
Did
movie.
they have like a terrible withdrawal from stopping that type of drug?
Well, watch the movie. They address that.
Awakenings?
Yeah. It's a good movie. A way to illustrate what's going on with the basal nuclei. That actually brings us to the end of what I wanted to cover. Okay. Let's see, the language stuff that I talked about last time, the brocas and all that, I usually do this time, but since I covered it last time, I don't have more to cover here. So I'll wrap it up there. If you have questions, feel free to ask them. And if you don't have questions right now, as you're preparing for things for next week, feel free to email or text me. But apparently we have questions. Go ahead.
Well, will you be doing grading over the weekend too for the,
I'll be trying to.
okay. Do you want to tell us like when you might be grading so we don't, I mean, obviously I'm not gonna wait till the last minute. I think there might be just like a section or two.
Oh, you mean like the part 1, 2, 3 things?
Yeah, I mean.
I'm gonna try to first thing every day get on and
Morning, okay.
check them off. But if you send me a text or an email if I'm available, I'll get on later in the day and try to do it. But
All right,
I can't necessarily do it.
The final still at 2:30, right?
So you guys are gonna come in Wednesday at 2:30, and you'll have until 4:20 if you need it. Technically, it's over at 3:25.
Oh.
I'll stick around if you need it.
Is there also an online component of the lab practical?
Yeah, it's in the practical.
Okay, that needs to be done beforehand.
Yes.
When you come in, I'm gonna, on this computer, turn off access to Blackboard. Everything needs to be done before you come in that day.
Got it.
Natalie, did you have a question too?
Yeah, I have two. So my other question is for, if you hyperpolarize the membrane of the neuromuscular junction, would that make it so a muscle would never contract?
I'm not gonna answer that because that's one of the questions on the
I
exam.
know, but it's so hard.
Wait, say it again, if you,
It's one of the questions, but I just like the view.
say it again, I didn't get to that.
So if the membrane in the neuromuscular junction, they